Hi all. So in today's class, we'll study about our IGBT, or simply we can say IGBT. So last two classes, we have studied about power diode, power MOSFET. Even though power BJT is not there in your syllabus, you have studied about BJT in your last semester in analog electronics. So some properties of BJT is required because actually IGBT is a combination of BJT as well as a power MOSFET. Okay, let's see in detail. So BJT, as the name says, it's a combination of, as we can expand it, insulated gate bipolar transistor, also called as IGBT, is actually something like a cross between a bipolar junction transistor and a field effect transistor. So IGBT can be roughly equal to IGBT is equal to BJT plus a MOSFET. So the properties of BJT and MOSFET will be combined. So we will have a combined benefit when we use IGBT for switching purposes. Okay. So this is an N-channel MOSFET. And this is so basically this shows the difference between N-channel MOSFET and IGBT. So in detail, we will see. This is just to make you understand how they are different in simple and structure and all. I have just given this here. So we will see in detail. So the basic structure is very much similar to that of a P MOSFET, except one layer, which is the P plus layer. There it was N minus and N plus layer, right? Except one layer known as the injection layer, which is P plus injection layer. So this is marked here, P plus injection layer. Unlike the N plus in the P MOSFET, it was an N plus substrate, if you remember. This injection layer is the key to the superior characteristics of IGBT. So because the main difference, I told you it's almost similar like a P MOSFET, but the difference is like it has an N plus injection layer, N plus substrate. So because of that only we have the difference in characteristic. So other layers are the drift and the body region. So here we have the drift region, which is an N minus layer. We call it the drift region. And then we have the body region, almost same as that of the P MOSFET. And we have two junctions, J1 and J2. So here J1 this junction, J2, we can say three junctions. J1 is a PN junction. Then again we have a PN junction here. Then again a PN junction here. So J1, J2 and J2. So predominantly we talk about J1 and J2 junctions. So N-channel MOSFET plus BJT. So bipolar junction transistors, there are two transistors here, Q1 and Q2. So we have a MOSFET here and then two transistors, Q1 and Q2. So Q1 is actually, if you see, it is so transistors are two types, you know, right? PNP and NPN. So Q1 is a P plus N minus P. P plus N minus P. This is P only, it's not marked. This is P only. P minus N, P plus N minus P. That is Q1. And Q2 is N minus P N plus. That is Q2. N minus P N plus. That is Q2. And RD, this is RD actually. So RD is the resistance offered by the drift region, and RB, this is RB, is the resistance offered by P body region. That is the body region, this P. So collector of Q1 is same as base of Q2, and collector of Q2 is, so you have seen N minus is common. So that is common for Q1 and Q2. That basically explains the structure. So P MOSFET, two transistors Q1 and Q2. So one is NPN and one is PNP, and then two junctions J1 and J2. Injection there is the main difference. So all these things you have seen. So gate, emitter, and collector it will be having. Okay. So now we will see how this can be represented in circuits. So the equivalent circuit we will see. So the collector path is directed, the current path is directed from collector to the emitter. So this is the collector and the current will go from collector to the emitter. The first path is called collector, there is P plus substrate, PNP to the emitter. So PNP to the emitter, N minus P to the emitter. So current can flow like that. This path is mentioned using the PNP transistor in an equivalent circuit. So we have this PNP transistor, this transistor, collector. This is the collector, PNP, Q2 transistor, P plus N minus P, that is PNP, P plus N minus P. So PNP transistor. That's the first part. And second part is collector, P plus substrate, N minus, so N minus P, N plus emitter. So that is basically N minus P, N plus emitter. Okay, so collector. So that's how the path is going. So we have the NPN transistor must be included. So Q1 and Q2, two transistors will be there. One will be PNP and another will be NPN, just like we have seen. So like the gate will be embedded in a metal oxide, silicon dioxide surface, then emitter will be there. So these properties are similar, just same as that of the power MOSFET. So only the main difference you should understand. And see, this is the gate pulse we are providing, and this is the drift region resistance RD we have seen. The body region resistance is not given here, but that also you can represent if you want. Okay, so this is basically the equivalent circuit. This is actually the exact equivalent circuit. We can have an approximate equivalent circuit also, where we use only one resistor, one transistor. So that's also available in textbook. So any one is enough. So this is the exact equivalent circuit. Now let's see how it is working. So already I told you the current path, how it will be. So what happens when we are providing the gate pulse? Let's see. So when the collector is made positive with respect to emitter, IGBT gets forward bias. So this is collector. So this collector, when it is made positive with respect to the emitter, this IGBT get forward biased. The PN junction will get forward biased. With no voltage between gate and emitter, two junctions between N minus region and P regions are reverse biased. So this J2 will be reverse biased. So now current flows, because if you are not providing the gate pulse, then it will be, the junction will be in a reverse bias condition, and as a result of that, no current will flow. So you might observe this is exactly same as what we have done for a MOSFET. So let's see, we are providing the gate pulse. When gate is made positive with respect to emitter by the voltage VG, so this VG, the gate is becoming positive. So just like that, this layer will become polarized, similar to MOSFET. So I'm not explaining. The last video you can watch. The gate emitter voltage more than the threshold voltage. So when this VG is made greater than VGT, that is threshold voltage, that is the minimum voltage that is required for getting polarized. So when gate is made positive with respect to emitter by voltage VG, the gate emitter voltage more than the threshold voltage of IGBT, an N channel or inversion layer is formed. So you can see here an N channel is formed, an inversion layer is formed in the upper part of P region just beneath the gate. So here you can see. So the current the electrons can move from one point to another here. So N channel short circuits, that's what I'm saying. N channel then short circuits the N region, N minus region with the N plus region, N plus emitter region. Okay, N plus emitter region and N minus region becomes a short circuit, and electrons from the N plus region begins to flow to N minus drift region. So from here, N plus region, the electrons will flow from N plus region to the N minus drift region through the N channel. So current will be in opposite direction. So opposite direction electron flow, right? So electron will flow from N plus to N minus drift region, and that's why we have the current path like this. As IGBT is forward bias with collector positive and emitter negative. Remember that. Reverse bias means collector is made positive and emitter. So IGBT will be forward bias, but with no gate voltage, it will be junction will be reverse bias. So IGBT is forward bias with collector positive and emitter negative. P plus collector region injects holes into the N minus drift region. Just opposite. In short, N minus drift region is flooded with electrons from the P border region and holes from the P plus collector region. With this injection, carrier density in N minus region increases considerably, and as a result, conduction of N minus region enhances significantly. So what is happening? N minus drift region, so this is the N minus drift region, is flooded with electrons from P body region and holes from P plus collector region. So as a result of that, there will be a higher injection of drift regions. Injection carrier density in N minus drift region increases considerably. So as a result, the conductivity is enhanced. IGBT gets turned on and begins to conduct forward current IE. So this will be the forward current IE that is flowing to the emitter. That's why we gave it IE, emitter current. Now let's see the VI characteristics of IGBT. So this circuit diagram is already familiar for you. I have already explained. So relation between the collector current IC. So you can see here, this is the collector current IC and the collector emitter voltage. Collector emitter voltage VCE. So IC and VCE. Actually VCE only. So IC and VCE at different levels of gate. So the amount of gate pulse we are providing at different levels of gate, that is VGE. So we have VGE less than V threshold value. So there is a minimum threshold value. The gate pulse should be more than the threshold value. The IGBT at VGE less than VGET, the IGBT is in cutoff mode. So the less than value, the IGBT is in the cutoff mode. And the collector current will be zero. That's we're not getting the output because the gate pulse is not present there at any VC for any collector to emitter voltage. So at VG greater than the threshold voltage, the IGBT goes into the active mode where the collector current IC increases. So you can see that VG1, VG2, the collector current according to the magnitude of the gate to emitter voltage, the collector current is increasing. Further, for each VGE, where VG1 is less than VG2, is less than VG3, the collector current is different. You can see the collector current is different for different values of the gate pulse. So this actually shows the VI Chara, output collector current and output collector to emitter voltage for constant for different values of gate emitter voltage. Okay, so this is roughly the gate emitter. This will be same as VG early. VG early. Yeah. So that explains the static IV Chara, or we can even say the output Chara. Now, what about the transfer Chara? The transfer characteristics of IGBT shows the relation of input voltage VGE to the output collector current IC. VGE to IC. When VGE is equal to 0 volt, there is no IC and the device remains switched off. So just as I told you, when the VGE is slightly increased but remains below threshold voltage VGET, the device remains switched off, but there is a leakage current. So small amount of current will be there. And when VGE exceeds the threshold limit, the IC starts conducting the current, the collector current starts to increase and device switched on. Since it is a unidirectional device, the current only flows in one direction. So VGE should be greater than VGE threshold, then the collector current will begin to conduct. That is a transfer Chara. And then output Chara will be collector current versus the output voltage, that is VCE, for constant values of input gate current, VGE. Different values of gate current. Then the collector current will have different values. That basically explains the VI Chara. So this is the circuit diagram, static VI Chara and the transfer Chara. So this, you can expect this as a question. Now this actually shows a practical figure of an IGBT with the same symbol which you have an emitter, gate, collector. You can see two transistors. So only one transistor is shown here. So you can see there is an equivalent circuit. So this is the same circuit here. This will also have a collector, gate, and emitter. Now let's move on to the switching Chara. So switching characteristics of IGBT. So when we consider the switching characteristics of IGBT, you can see that we have a VGE, which is gate emitter voltage. So you should check the circuit also. So whatever I have marked here, so circuit we have been discussing for many times now. So it should be clear for you. So let's see. So VGE with respect to time, that is gate emitter voltage is there, and then collector current with respect to time, and then we have the VCE, the collector to emitter voltage. So turn on time, T on, is composed of two components. So turn on will be composed of two components, that is T on will be equal to, you can see here, TDN plus TR. So TDN will basically be a delay and TR will be the rise time. So delay time is defined as the time in which the collector current rises from leakage current ICE. So we have the leakage current ICE here, and from here the collector current is increasing. So from ICE it is increasing to 0.1 IC. So you can see here, the collector current is increasing from ICE to 0.1 IC, and that time is called the delay time. So that is the delay time. And rise time, of course, you can see 0.1 to 0.9, which the collector current rises from 0.1 of the collector current to almost IC, but and collector emitter voltage falls from 0.9 VCE to 0.1 VCE, same thing. So voltage is falling from 0.9 VCE to 0.1 VCE, and current is increasing from, collector current is increasing from 0.1 to 0.9 IC. So that is the rise time. This is the rise time. So overall it is T on TD plus TR, and we are providing the gate pulse VGE. And turn off actually consists of three components. So T off will be equal to TDF plus we have a TF1 plus TF2. So TDF, TF1, TF2, everything is marked here. So let's see what is delay time, TDF. Delay in falling, what is happening? Is defined as a time when collector current falls from IC, basically 0.9 IC, to 0.9 IC. Falls from IC to 0.9 IC, and VC begins to rise. So you can see VC is slowly beginning to rise, and the collector current is slowly falling. IC to 0.9. So here it's slightly increasing. So this is TDF. And initial fall time TF1. Initial fall time TF1. That is 0.9 to 0.2 IC. So everything is clear. And emitter rises, voltage rises to 0.1. This much, 0.1. And final fall time. So this is the final fall time. So I have given these notes here. Don't worry. So final fall time means 0.2 IC to 0.1 IC, and 0.1 VC rises to the final value of VC. So this is basically the switching Chara. So what's happening when the switch goes from on to off? That is when we are giving a gate pulse and the switch is becoming on. So just like I have given notes everywhere, because power electronics is actually theory plus problem subject, numerical subject. So first of all, you should understand the theory in depth, because power electronics you're studying for the first time, right? So I have given everything here. You can write down the notes. So working also, I think I have beautifully arranged it here. So you can study, listen to me, and then write the notes also. So everything is given here. So I hope everything is clear for you. So just like we have studied MOSFET, power diode, and then BJT also slightly have explained. So this sums up the basic switches. So you should be clear about the switching Chara, then the transfer Chara, output Chara, then what is the working structure of all the things. There is IGBT, power MOSFET, then BJT, power diode, etc. So in next class, I will give you a comparison of all the there is MOSFET, IGBT, and then BJT. Thank you.